Hi folks, we're going to do a little quick review on this idea of determining the symmetry of a function. So there's two types of symmetry that are of interest to us. So first is what we call even symmetry, or what the textbook refers to as line symmetry. Okay, and when the line they're talking about is the y-axis. All right, so here even symmetry looks like this. So it could be function like this has even symmetry because it's symmetrical about the y-axis. But when we're trying to determine symmetry, we want to do so algebraically. So recall that the idea is if I take any x value and then I consider the x value with an opposite sign, they should produce the exact same y value. Okay, so in other words, f at negative x needs to be equal to f at x. And this is what we're going to use to determine that symmetry. Then we've got odd symmetry, okay, or what the textbook calls point symmetry. All right, and the point that they're talking about is the origin. Okay, so here if we take an example of something that has odd symmetry, so y equals x cubed, okay, the idea is that if I were to rotate this 180 degrees about the origin, I would get the exact same function. But again, we want to think of this algebraically, so we'll do the same thing. Take any x value and then take the x value with the opposite sign, and we see that the y values are also opposite in sign. So in other words, f at negative x is equal to not f at x. They're not equal, but they're just opposite signs to each other. All right, so if a function can be shown to have this property, then it's even, and if a function can be shown to have this property down here, it's an odd function. All right, so in both cases, we see that what we need to work with is f at negative x. Now, very importantly, it's not enough to just pick any x value like 3 and then compare it to f at negative 3. Okay, because those are just two particular points on the function. We need to show that this is true for all x values. So the best way to do that is to not pick a precise one. All right, so I'm going to start by doing this. So this is what you should be following here. So here's my function. What I'm interested in doing is determining f at negative x, simplifying this, and then comparing it to the original function. All right. So here, what do? Wherever I see an x, I'm just now going to replace it by negative x. So 3 times negative x to the 5th minus 4 times negative x. And now we're going to simplify this. So when I have an odd power to a negative, it remains negative. So this can be simplified to negative 3x to the 5th. And then negative 4 times negative x is going to be plus 4x. All right, so now comparing f at negative x with f at x, clearly they're not equal to each other. Okay, so we know that it's not an even function. But if I were to factor out this negative in front of the 3x to the 5th, okay, I will get something that looks like the original leading term. So let's do that, factor out the negative 1, but of course I can't just factor out the negative 1 from the first term, I have to do it from both, and so here I'm left with minus 4x. And this is where we realize that this expression inside the bracket is exactly equal to f at x. So what I've shown now is that f at negative x, regardless of what the value of x is always going to be equal to the negative of the original function. Okay, so our conclusion here is that f is an odd function, or of course you can say that f has point symmetry, okay, if you want to use the textbook's vocabulary. All right, in the end, what it comes down to is if you need to test the symmetry of a function, you input negative x, simplify, and then compare to the original function. If they're equal, it has even symmetry. If they're odd, if they're negatives of each other, that has odd symmetry. And if neither of those two things occur, there's that third option, which most functions fall under, is that there's no symmetry at all. Okay, that's it for this one.